Whether you're gearing up for your engineering finals, FE or PE exams, or getting ready to teach an engineering course, thanks for dropping by during my office hours. Today, we'll explore the application of the Moody diagram in calculating the friction factor for determining major head loss. Darcy-Weisbach equation is often used to estimate the major head loss in a pressurized flow of fluid. In order to use this equation, we need to know the distance traveled by the flow L, the pipe diameter d, the mean velocity of the flow v, the gravitational acceleration g, and most importantly, the friction factor F. The calculation of friction factor begins with the determination of the flow regime using the Reynolds number. If we found the flow to be laminar, as implied by a small Reynolds number, we will be able to calculate the friction factor using a very simple equation, F equals to Reynolds number divided by 64. This equation is derived directly from Newton's second law. The calculated friction factor F is then used to determine the major head loss HF. However, if the flow is turbulent, we won't be able to derive any theoretical equations to calculate the friction factor F considering the complexity and unpredictability of turbulences. In this case, we will rely on empirical equations that can best fit with the experimental data and observations. One of them is the Colebrook-White equation. We have discussed how to use the Colebrook-White equation to determine friction factor in our previous video. At the same time, we also pointed out that a serious challenge of using the Colebrook-White equation, as well as many other empirical equations for turbulent flows. The calculations can be very time-consuming without the use of modern calculators. In this circumstance, the use of a graphical solution, known as the Moody diagram, becomes extremely appreciable. The Moody diagram specifically aids in determining the friction factor for pressurized pipe flow. The friction factor is charted against Reynolds number and relative pipe roughness on the Moody diagram. Relative roughness is defined as the absolute pipe roughness epsilon divided by the pipe's inside diameter d. Meanwhile, Reynolds number signifies the balance between inertial and viscous flow effects. Turbulent flow is denoted by Reynolds numbers greater than approximately 3000, while values lower than about 2000 indicate laminar flow. To interpret the Moody diagram effectively, start by calculating the pipe wall's relative roughness using the pipe's absolute roughness divided by its inside diameter. Typically, the absolute roughness can be sourced from literature based on the pipe material. Once the relative roughness is established, locate the nearest curve of constant relative roughness on the right axis of the Moody diagram. When the relative roughness falls between two curves, interpolation might be necessary. Next, compute the Reynolds number for the flow, as outlined in our previous video. Then, identify the point where the curve of relative roughness intersects with the calculated Reynolds number. Finally, trace horizontally from this intersection to the left axis to determine the friction factor. In cases where the intersection falls between two friction factor values, estimation may be needed. The accuracy of estimating the friction factor using a Moody diagram hinges on two factors. 1. The ability to interpolate between relative roughness curves. 2. The precision of the value of the pipe's absolute roughness. Careful use of the Moody diagram or a Moody diagram calculator can minimize interpolation errors. However, an erroneous absolute roughness value can lead to inaccuracies in both numerical and graphical approaches for determining the friction factor. Thank you for tuning into this video. If you have any questions or specific civil engineering topics you'd like me to cover in future videos, feel free to leave a comment below. Your likes and subscriptions motivate me to create more content, ensuring you don't miss out on future updates.